Don't forget to like, share and subscribe my YouTube channel. Now let's see today about torque. Equal forces are exerted on both sides of the lever. As a result, it is just balanced. If we raise one side, like this one, the forces are still equal when it just leave to just return back to its original position. So what pulls back to the horizontal state? The force that makes the unbalanced one just removed, then the system becomes balanced. Before we answer that, let's demonstrate the concept of torque, moment and moment of force. If we extend the lever to the right, you see, as the lever just increase the distance, you can see it is just falling to this one because the rotational force is just greater, tau. It is areas of the purple rectangle that determine whether the lever is balanced or not. We can restore the balance by adding another weight. You see, when you just add another weight, this rotational effect should be just balanced. Each purple rectangle represents a torque, a more accurate definition to follow. Now back to the original question. So let's raise one side again. See, just unbalanced. As the torque is balanced now, you see here, note the lever hangs slightly below the pivot. To see why it's important, let's pull it even further down. You see, as we just move further, nothing will be just happen still. Now it's clear that the torques are not balanced here, because another extra force is just added. This is what pulls the lever back to the horizontal state. Now let's revise the things that we have seen here. In linear motion, linear or translational motion, you can, Newton's second law of motion is force is equal to mass times acceleration. In rotational motion, this is rotational dynamics and this is linear dynamics. In rotational dynamics, there is a torque. This torque is just defined as R vector crossed with F, which means the magnitude of tau is equal to R vector and magnitude of F and the sine of theta times n. For the maximum torque to be happen, theta is 90 degrees. Therefore, tau becomes R times F times the sine of 90 degrees. Then tau is equal to R times F. From Newton's second law of motion, we have that force is equal to mass times acceleration from this. So tau becomes R times m times a. This acceleration is just given by that alpha is equal to a over r, where a is equal to alpha times r. Then one can write here r is equal to m times alpha times r, where tau is equal to mr squared times alpha. This is the physical quantity that we defined earlier, and it is known as moment of inertia. Then tau is equal to inertia times alpha. You see here, in Newton's second law in linear motion, we have that the acceleration is directly proportional to force, and the acceleration is inversely proportional to the mass. The same thing here holds true. That is, the angular acceleration is proportional to the torque, and the angular acceleration is inversely proportional to the moment of inertia. Just this representation should just tell us a lot of things about this one. Also, this can be just correlated with other physical quantities, which means the torque is equal to, in place of what is known as moment of inertia, and alpha is equal to omega minus omega naught over t, where tau is equal to inertia times omega minus inertia times omega naught over delta t, where tau is equal to, this is known as the final angular momentum, that is L, minus This is the initial angular momentum divided by the time t. This is just the same as change in L to change in t. So the change in the net torque is directly proportional to the angular momentum and inversely proportional to the time. When you just cross multiply this one, we can get that tau times delta t is equal to change in L, which means this physical quantity is equal to this one. This physical quantity is known as angular impulse. It is just denoted by J. This is just delta L. Therefore, one can say that the angular impulse is equals to the change in angular momentum. This relation can be just holds true. In translational motion, you can have that the work done is equal to F times S. In the case of this one, work done is equal to what is known as F times S is just exists, but F times in place of S, since theta is equal to S over R, then S is equal to theta times R. This is theta times R exists. This is F times R times theta. And earlier we defined that Fr means what you call the torque. This torque times theta is just exists here. So this is the definition of work done. Here in rotational motion, in translational motion, that we have seen that the work kinetic energy theorem, it also exists in rotational motion. Now let's take different examples about this topic. Using a screwdriver, you try to remove a screw from a piece of furniture, but can't get it to turn. To increase the chance of success, you should use a screwdriver that, you see, you have two physical quantities are just important for a rotational effect to produce tau. One is the force you applied. The second one is the distance r. If you just take these two cases, since you are just applying constant force, the one you have, if you have two screwdrivers, one is just has a handle which is just thicker or what is wider in shape. This is just the screwdriver has wider handle and the other one has smaller handle here. When you just hold by use your hand and to turn, to increase the torque, either you increase F or you increase R. Since your force is just constant, you can see here that the one that which has a fat or what is known as a wider handle can be used as larger radius. Since it has a larger radius, when you applied a force F, in the case of this one, tau should be just tau as R increases, it will increases. So therefore we can say that the one which has a wider handle has, like this one, can produces a chance to a good success in opening or in removing out the screw from the screw from using by a screwdriver. Which of the following statement is correct? A. When an object is rotating necessarily, there must be net torque. When a bicycle wheel replaced by a wheel of larger diameter, its angular velocity unchanged. When a bicycle wheel replaced by a wheel of larger. Now the question here is, when an object is rotating, necessarily there must be a net torque. No, net torque is not. If in the absence of net torque, body can be just moving with constant speed or with constant angular velocity. So this doesn't satisfy this one. When a bicycle wheel is replaced by a wheel of larger diameter, its angular velocity unchanged. Yes, angular velocity does not depend on, not dependent on radius. So B is just the answer. For a diver to make 2 or more R turns while the air high, he must stretch his legs outward. For a diver to make 2 or more turns. While in the air, he must stretch. No, he must not stretch. He must have to pull or contract his body and can just turn 2 or 3 times. The change in the axis of rotation of an object will not change its moment of inertia. The change in the axis of one of the situation that determines the moment of inertia of a body is the axis of rotation, or its orientation is just exists. So the answer is just gone to choice B. This is just the answer. Next, a force 20I minus 15J Newton rotates a bar at a position of 0.6 I. What is the torque of this? Now, torque is equal to R crossed with F. That is I, J, and K. And the determinant factor, we can just put it here. R is 0.6, 0.8, and 0. That is 20 and minus 15 and 0. So you can get here I times this one is 0, and this times this one is 0, and minus J. This times this one is 0, and this times this one is 0, plus K. 0.6 times this one is minus 9, and 20 times this one is minus, this is just 16. This is Newton meter, which is just the same as here is 0 and here is 0. And when you add this one, this is minus 25 K and Newton meter. When you say Newton meter, this is not joule, because there are two different physical quantities. That is energy, and this one is not energy. A turbine having a moment of inertia of 8 kg increases its angular velocity from 10 rad per second to 20 rad per second in 4 seconds. Then which one of the following statement is correct? The angular displacement A, theta is equal to omega naught plus omega over 2 times t. This is the distance traveled, the angular displacement. Omega naught is 10 plus 20 divided by 2 times 4. Then this is 2, 30, 60 rad. Yes, this is true. B. The net torque acting on is, how much is the net torque? Net torque can be just determined by, first let's find alpha. This is omega minus omega naught over 2 over delta t. This is omega is 20 minus 10 over 4. This is 2.5 rad per second squared. Now theta tau is equal to inertia times alpha. Inertia is just here 8 kilogram meter squared. This is just the moment of inertia, and alpha is 2.5 rad per second squared. This is just the same as 20. 8 times 5. 8 times 5 is 20. This is 20 Newton meter. So this is not the answer. C. The work done. Work is equal to tau times theta. That is tau is 20 Newton meter, and theta is 60 rad. per second. This is just the same as 1200 joule. It's not the answer here. D. Rotational power. Power is equal to work done over time. The work done is 1200 joule and the time is 4 seconds. This is 300 watts. So this is not the answer. So the answer is just choice A. Consider a spanner here. This is a spanner. It is just used to move a bolt to rotate here. If you apply a force, which point may give greatest torque? You see, this is the point where it just rotates, about this point. Now, if you just take here, tau E1 is equal to here, this is tau 2, and here is tau 3, this is tau 4. You can take here, this distance is, let's take R1. This distance is just, let's take R2, and let's take this distance is just R3, and let's take this distance is distance is R4. Now in each case you can get what is known as the greatest torque. Tau 1 is equal to, the force is the same, F times R1. Tau 2 is equal to F times R2. Tau 3 is equal to F times R3. Tau 4 is equal to F times R4. Then what can you see here? Tau 1 is tau 1, tau 2, tau 3, and tau 4. Which one is larger here? In all cases, you can see tau 4 is greater than this one greater than this one. So 4 is just largest value for this issue. So this is just the answer here. As the length distance from the rotational axis increases for a constant force, the torque is just increases. Which one of the following is the rotational equivalent of Newton's second law? Newton's second law is just force is equal to mass times acceleration. Then which one is just the equivalent one? This is not omega. The mass, in place of mass, you can have that moment of inertia. In place of angular acceleration, you can have linear acceleration, you can take alpha. This is just the same as tau. So tau is equal to inertia times alpha should be just take place. This should be just holds correct. Thank you for watching. Don't forget that to like, share and subscribe my channel. Thank you for watching. Enjoy more than 200 videos of physics here from elementary to freshman program.